And maybe we can start now. So my name is, can you hear me well, first of all? Yeah? My name is Egor Zakharov. I work in Samsung AI Center as an engineer and do PhD at Skoltech. And today I'm going to talk to you about generative adversarial network. This will be a kind of introduction to the topic, but with some more advanced parts so that you would be actually interested in the lecture. So the outline of the talk is following. We'll have two parts, and in between, I believe we'll have a small break. So the first part will be a more theoretical one. So I will give a brief introduction, from intuition standpoint into what GANs actually are, and then we will discuss, basically the theoretical backbone beside that. So the divergences, and we'll cover a bunch of those. In the second part of the lecture, we'll talk more on the practical side, but also with a little bit of theory, so that you could actually understand why actually these tricks that made the GAN training so much more stable and the results so better in the past few years. So what is the theory behind these tricks and why do they actually work? And in the end, we'll talk a little bit about the quality measurements, so what you could do to actually measure the quality of your trained GAN model, and, some applications, practical applications. So we'll start with part one. And to get you started, so let's consider a simple classification problem. So we'll have two distributions, P of x and Q of x, defined on the same support x. One distribution corresponds to class 0, another one to class 1. And at each point, we can evaluate the probability of these distributions. So what would be the optimal classifier that would separate these two distributions? So it will predict the probability of label 1, and what would it look like? So it turns out the formula is following. So it's a ratio between Q of x divided by P of x plus Q of x. So it looks like this. Essentially, it tells you the probability of a given x belonging to class 1. And now there is a question. So what could we do to use this classifier, to use the output of this classifier in order to make these two distributions aligned? So in theory, what we would like to get after, for example, let's consider Q of x to be the distributions of fake samples that are generated by our model. So in theory, we would like to get this picture. So this distribution would correspond to the distributions of P of x, the real samples. And in that case, the classifier would be just equal everywhere. It would be 0.5. So what could we actually do to use that output of the classifier to drive one distribution towards another? Well, the answer is quite simple and intuitive, right? Where the output of this classifier is above 0.5, we would like to push the probability distribution down. And where it's below 0.5, lower than 0.5, we would like to push it up. So the intuition is simple. And if we do that, so we would actually make these distributions align with each other and match with each other. So this is like the intuition of how the GANs actually work. So they try to use the output of some classifier in order to push one distribution toward the other and to make them match. And the cool thing is that in order to train that classifier that we use as a feedback tool, we only need samples. So we don't need the access to these distributions. So we don't need to evaluate the density. We only need the samples. But the problem is that if we want the distribution Q of x to be like the distribution of samples from our generator, the distribution that we could sample from, so how do we actually model that? And there are two approaches. Well, the first of all, let's try to parameterize that distribution. So let's say that this distribution is a parametric function. For example, it belongs to a family of, let's say, normal distributions. Well, in that case, even for some more complicated families of distribution, we could still perform the sampling, but the main point is that we would be able to also evaluate the density. And this is one of the approaches. But the alternative approach that actually GANs utilize is to define the distribution Q of x implicitly. So we don't parameterize it with some function. Instead, we parameterize a mapping from some distribution that is easy to sample from, for example, some normal distribution. And essentially, this mapping is just a deterministic function that maps one domain, Z, to another domain, X. And in that case, sampling is always easy, because in the case of parametric density function, it could be, well, the sampling process could be inefficient. For example, we could resolve to some sampling methods in order to get samples. But here it's just straightforward, because we just sample from a simple distribution and then map it to the target domain. But it is hard or even impossible to evaluate the density of that function. So especially for the high-dimensional X, it's actually, well, maybe even an unsolvable problem. So these are the trade-offs between these two different approaches. And we'll take the second approach and explore what it actually yields to us. So in the case of images, it actually looks like this. So we take some noise and map it to these diverse images. And the goal of this model and our goal is to actually make these two distributions, distribution of images and distribution of noise, somehow aligned. So we, mapping this noise, we actually cover the whole space, for example, of realistic faces. And well, let's take a look at the simulation of what actually happens if we use the feedback of that classifier to train that parametric sampler. So the training looks like this. So the classifier is constantly being updated to the new samples from Q of X, and at some point we get stuck, but the samples, they actually kind of correspond, at least in their support, to the distribution P of X that we try to match. And let's discuss how this machinery actually works behind this example. We have a classifier. Before, we consider the classifier to be optimal. But since we don't have access to the densities, we just parameterize it with some, well, it's a parametric function, essentially a neural network. And this neural network outputs the probability of a data point X belonging to class 1. So we train that classifier with a classification loss. And as you take a look at it, it's actually, you don't see my cursor, but OK. It's actually a binary cross entropy. But in binary cross entropy, we have one expectation because we have the data point X and Y. So the probability distribution is joined on both X and Y's. But here we just separated it into two expectations. In the first term, the Y is always equal to 1. And the second term, the Y is always equal to 0. So as you can see, it's all it takes for us to actually train that model. So the algorithm that was behind the previous example is following. First, we try to update that classifier in order to make it closely resemble this optimal classifier that we talked about before. So we find the minimum of that binary cross entropy. And then we use that feedback, so the gradient, in order to update the generator that tries to maximize that function. So we want to make the classifier being as suboptimal as possible. So we want it to essentially output random guess. So we want to increase its loss. So we take a step, basically perform gradient ascent with respect to that function. And we repeat that process all over again till we get convergence or at least are satisfied with the results. But we can take a more general look at that scheme, because on the first step, we don't specifically need that binary cross entropy or treat that problem as classification. We actually can treat it as an estimation of some update guide for our method. For classification, it's like the first formula where we divide P of X by P of X plus Q of X. But we also could use some other, basically, values that measure how distant these two distributions are from each other. We could take just the ratio between these two distributions. We could take the difference. Or we could take any distance function, the divergence between these two distributions. Just evaluate it, and then use it as a guide to update our generator and move the generator distribution closer to the true distribution. And we also repeat that process. And and to build on that intuition that we had before, so more specifically the difference between the models. So before we said that we could also parameterize either the density function or this so-called mapping function. And this is actually a big difference between these two classes of models. So the first group of models, we call them prescribed models. And well, you can think of VAEs, for example. In VAEs, you have direct access for both prior, you have the access to likelihood of the sample. You can also evaluate all these conditional distributions as well. So you have not only ability to sample, but you also have access to the density functions. And this may be useful to some problems. But in case of GAN, you can evaluate and sample prior, but for posteriors, you can only sample. So it's kind of restrictive. And what you can do, you can evaluate expectations, like we did in the previous slide, where we considered the game. And, well, you can kind of approximate these distributions, but that is not used on practice. And, well, this is like a very... you may think of it as a bad trade-off, right? Because we trade off too much considering compared to VAE's models. But on practice, that actually results to much better qualities of samples. So if you are aimed just at quality of samples, and well, another thing we'll discuss closer to the end of the lecture, what you can actually get from GAN models. Then you can resolve to them. If you want some statistical inference to run, then you have to resort to the models that actually allow you to evaluate the distributions. So let's take a look at the game that we discussed before one more time. Here, we can actually swap the sign of the function. So before we did one minimization problem with respect to the discriminator and maximization problem with respect to the generator. Well, not discriminator, but classifier. But essentially, these terms are the same in our context. And actually, if we just flip the sign and reverse that optimization problem, what we get, well, we can rewrite this as actually a divergence between the two distributions. It's called Jensen-Shannon divergence. It's a particular form of divergence. And you can view it as estimation of a kind of divergence between the two distributions and minimization, the distance between them. So even the original objective that was used in GANs, well, which is essentially a classification objective, is actually also can be written in the form of some divergence. So this intuition is a pretty strong one. And, well, so this can be considered as a game of some sort, right? So in the first step, you are trying to, essentially, this turns into a min-max problem, right? You try to minimize the objective that the classifier or discriminator tries to maximize. And this objective is a divergence between the two distributions. And we can actually use a huge array of different divergences between the distributions as actually this function that will guide the, well, the matching of the, well, essentially guide the updates of the generator. And, well, we'll consider two classes of divergences, the so-called F-divergence and, well, Wasserstein Distance. And so F-divergences, for two distributions P and Q defined on the same support, the divergence is, well, the class of F divergences is following. So we just take the function F from the ratio and multiply by Q of X. Remember that earlier we said that all these quantities, like ratios between the two distributions, classification score, well, they all kind of about the same. So they're all measuring some distance. And we're just free to choose any of these quantities for our applications. So if we substitute different functions f into that formula, we'll actually get different forms of divergences. For example, KL divergence, reversed KL divergence, well, total variation. So essentially, there are like multiple papers that try to explore different sorts of distances, what objective can be used to optimize. They have somehow different properties, but what I want you to actually know that there is a huge array of possibilities that you can explore in your applications. And well, even if some objective cannot be rewritten as a divergence, it does not mean that it is a bad objective. because some, modern applications, when we apply GANs to some state-of-the-art models, they don't actually use objectives that can be rewritten as divergences, or at least we don't know what divergences they correspond to. Next, I would like to talk about Wasserstein distance because, Wasserstein GANs, they are kind of underutilized recently, but they're still good models, especially when you have small amounts of data. In order to introduce you to this metric, let's consider a different problem. Well, its problem is kind of related to what we considered before. So we have two distributions, x and y's. So these are like densities. And we would, they're not specific densities. Consider of some, storage, for example. You have one storage facility and another storage facility. One set of storage facilities and another set of storage facilities. And you want to transport goods from one set of storage facilities to match the new one. And you have basically a cost of transportation. So maybe it could be related to the distance between these two facilities, right? It could be just the norm of x minus y. And then the optimal transport is just a function that depends on the distribution of goods in these facilities. So it depends on the distribution P and distribution Q. And it is infimum over gamma, and we'll discuss what gamma is. It's essentially a joint distribution on distributions of that expectation, so of expected cost of the transporting from one set of facilities to the other. So gamma is, is a distribution which marginals correspond to corresponding P and Q. So you can see it here. Okay. So in the last line. And what gamma actually is, for example, in discrete case. So on the left side, we have, for example, our, it's already closer to our example. So we have the distribution of some real data, and this denotes lines, and the columns denote the distributions of some fake data, the parameterized data. And gamma actually tells you how much do you want to take from one column. For example, if you consider this column, so it actually tells you how much are you going to store in this column, which is not going to move anywhere. And if we sum up over the lines, we get the total amount of goods here. If we sum up of the columns, we get total amount of goods here. And this, for example, square tells you that you are going to actually move some stuff from that column to that column, so to a different one. And essentially, all the diagonals are non-zero, but they're just too dim to see. So this is kind of a transportation plan. And each of these transportation plans actually has its associated cost, because we can evaluate all these non-diagonal elements and calculate the cost of the transportation according to that plan. So this is like the primal problem for optimal transport, the first line. But of course, it is infeasible to solve it, because we have to optimize, essentially find a minimum, find a finum over the space of probability distributions. And we don't have access to the densities, but also it would be quite hard. So instead of considering the primal problem, we can go to the dual problem. So I'm not going to delve into too much details about the optimization theory behind that. But for that primal problem, you have a dual problem, and if you solve it, then under some conditions, you get the optimal solution. And, but you have to trade off something when you go to the dual problem. For example, here we have some intractable set over which we want to optimize. But, but there are no restrictions inside that set. When we go to the dual problem, we have a simpler set, a simpler problem where we actually have a function f. So it's supremum of this simple quantity. So we just want to sample the values from real distribution and evaluate some function f, and then subtract the values from fake distribution and evaluate the same f. F can be parameterized. It's essentially a classifier or discriminator. But here we have a constraint. So f has to be, at most, Lipschitz 1 continuous. So the Lipschitz constant has to be at most 1. Lipschitz constant defines how, essentially, Well, it's something in between the continuity and smoothness. So it's something in between. We'll talk about it more in depth when we consider the techniques closely related to that Lipschitz continuity. But now we're just interested about how to satisfy that condition. So there are two options. First, that we can consider, that we have considered in the original paper, and that I don't really want to explore because this is kind of obsolete. So you will try that in the seminar. You will see if it works better than the solution proposed later, but still it's weight clipping. So essentially, we can just clip the weights of the network and hope that the output of the network for similar points do not deviate much. So of course, if the network always outputs 0, its output will be always close for any input. But if we clip the weights, if we make the weights small in the magnitude, we can hope that this output will be constrained in some sense for any two input points. And this is what the motivation in the original Wasserstein GAN paper that they used. And a more advanced version of that is a gradient penalty. So I'll briefly go through what actually is here. So we evaluate expectation over the set of x tildes. X tildes are actually a convex combination between real and fake data points. So we essentially sample a parameter from 0 to 1. Well, basically for any two real and fake points, you just sample them, you draw a line through them, and you just take any point along that line. So it's kind of a convex hull over these points. You sample from it. But instead of like enforcing Lipschitz 1 continuity, you're actually enforcing the gradients of the discriminator to be 1 almost everywhere. So of course, if you do that, you'll get Lipschitz continuous function. But, well, it's a too strict requirement. So, well, on practice, it's a more strict constraint than the one used in this supremum objective. But the authors proven in their paper that the optimal transportation, function f, it actually satisfies that condition below. So you can actually enforce it, and you will not change the optimal point. We'll discuss that gradient penalty and Lipschitz 1 continuity further in the lecture. For now, let's compare the divergences that we discussed before. Well, actually, so here on the left, we consider the two distributions. One distribution is a delta function at 0, so it always returns 0. And another distribution, Q, is a delta function at theta. And theta is like a parameter. And if we evaluate these distances, so Wasserstein distance behaves quite nice, right? We get, before we set that, we want to use these divergences in order to train our model. So what do you think? Which the training signal actually makes more sense? Yes?
I have a question. So in the gradient penalty, you have a D. So that's the divergence. But then is it the same as the T that's there in the two lines above, like in the previous slide? So is the D the same as the T here?
You mean, is this W the same as T?
No, I mean, is the T in the first and the second equation the same as the D in the last formula at the bottom of the slide? So
you mean this expectation, is it different from this expectation?
Yes, but then is the D the delta X?
Yeah, I'm sorry, I mislabeled them. So F and D are actually the same.
F and D are the same.
Yeah.
Got it. Yes, thank you.
Apologies. And so which distance metric actually, makes more sense, gives more feedback to the generator how well it behaves? Well, if you look at this, actually, Jensen-Shannon divergence, it will give you just constant response. KL divergence will give you infinity, so don't use KL divergence. Wasserstein gradient penalty kind of behaves a lot better, so it gives continuous signal. And what it tells us that not all divergences kind of born equal, because this example may seem like degenerate, right? So it's kind of not non-practical. But on practice, consider the problem of images, generation of images. Images are actually a very high dimensional space. And the amount of data in the data set is actually finite. And there are papers that have proven that you can always construct an optimal hyperplane through that high-dimensional image space that would separate the two sets, the set of real images and the set of generated images. So we can always do that, essentially, under reasonable conditions. And so here it means that if we actually use, for example, the Jensen-Shannon divergence for the optimization, it will always give us some constant, and the gradient of that constant would be 0, so there would be no training signal. And this is kind of contradiction. So the theory that we discussed before, which is a common theory that's used to explain GANs, it actually kind of contradicts itself. And there are, well, we'll build on that contradiction even further when we discuss practical aspects of training of GANs. But this image is like, I would like you to maybe think about it. So how could we use the divergence to train a generator if this divergence is, in real scenarios, has to be always 0, the gradient of it? So there has to be much more to GANs and why they work than the common theory that is used. So the optimization of divergence, that narrative. So, well, now I'd like to go to the second part, but if you want, we can make a 5 minutes break or a Q&A session regarding that part. So what do you think? Break, or we continue after a small Q&A? So in the second part, I would like to talk about some, first of all, we'll start with some practical tricks that make the GAN training easier. And in the sense that you get better results more consistently. And these tricks were developed in the past few years. But we'll still consider theory so that you would actually know how these tricks work and why do they work. So we'll start with the first one, spectral normal, and I would like to point out that you have to always add them, essentially. There is no reason not to add these tricks into your network. So the first one is called spectral normalization. And essentially, it is also, like in Wasserstein GANs, it's about introducing Lipschitz continuity to the networks. But the gradient penalty that we discussed before on practice is actually a pretty strict constraint. So it constrains your optimization process too much. So it may make sense to that Wasserstein distance problem. But if we consider some other objectives, so you can apply essentially gradient penalty to any network that you train. For other objectives, it may be actually too restrictive, and it won't allow you to actually converge to the optimal values. And this is why it introduces, well, it's informal, but you may think of it as introducing some bias into your network. So your network will train better on smaller samples. It will not overfit, but it will not actually, if you have a large data set, it will not get the same quality as if you wouldn't use that gradient penalty in your training. And so, well, researchers thought about how to introduce that Lipschitz continuity in an easier way, and that wouldn't be as restrictive. Because as I said before, if you make the norm of the gradient equal to 1, that actually implies that this function is Lipschitz continuous, but you can get away with easier restrictions. For example, norm of the gradient less than or equal to 1. So it's actually easy to introduce Lipschitz continuity into a linear function, a linear operator, essentially a matrix that is multiplied by a vector. Make this Lipschitz continuous. And we'll discuss how on the next slide. And now let's think. So in a neural network, what layers do we actually have? So a neural network is a composition of some functions. So if we can make each of these functions Lipschitz continuous, then in total, the network will be a Lipschitz continuous function. So as I said, and this is like a hint, that linear operators can be made easily Lipschitz continuous. What about the nonlinearities? So there are some nonlinearities, for example, ReLU. It is their property that they do not increase this Lipschitz continuous factor. So if the function is Lipschitz continuous, and if you apply ReLU to its output, it will not increase this L. So we're good with some nonlinearities. But the layer that remains, and which is quite important, are actually convolutions. So can we make convolutions Lipschitz continuous? And let's remind ourselves with how they work. So we just take the input matrix and slide alongside it with some kernel. and we'll calculate the output. And let's formalize it a little bit more. So we have the input matrix X, we have kernel omega, and we want to convolve X with omega. So what we get in the result is quite simple to calculate. And as you can actually see, there are non-linear operations, essentially. You're just multiplying values from X by values of W. This is like a polynomial, but there are no second-order terms. So this is a linear operation, actually. And we can easily reformulate that operation, the convolution, as a multiplication of some matrix by some vector. And let's see, well, long story short, the matrix looks like this. It's kind of ugly, and the vector that we applied to, is just a reshaped version of our input matrix. So as you can see, the matrix A omega has the shape of number of output values times number of input values. And if we multiply each line by that tensor, we will actually get one of the items from the output of that convolutional operation. So what we want to do after this matrix by vector multiplication is just to reshape output matrix, and we essentially get the result of the application of convolutions. And most importantly, this matrix has been obtained only by rearrangement of the values from the convolutional kernel omega. So we didn't change anything, we just rearranged these values, and this means that we can differentiate through that. So if we would apply that operation to some input X, we would be able to differentiate through A omega with respect to omega, because we could just, get a lookup table and just sum up the gradients over the similar terms, like these K1s, K2s, K3s, etc. So now, in order to make the neural network, the typical neural network that we use that has convolutional operations, linear operations, and ReLUs, Lipschitz Continuous, you have to make essentially find out how to make linear operator Lipschitz Continuous. So this is the definition of Lipschitz Continuity. So we have some function f, and with respect to some norm, I took the second norm, but it's essentially equivalent. So we could take any norm. This inequality has to hold for any x and 1 and any x2. So this is the definition. Instead of f, we have a linear operator A, essentially a matrix that is multiplied by a vector. And then we can rearrange this inequality a little bit. So we call x the difference between x1 and x2, and we divide by the right side. And since it holds for any x, as we stated before, we can put a supremum on the left side. So essentially, it's maximum. We substitute here the x that makes this quantity maximum. And this inequality still will hold. And it turns out that the thing on the left, it's an important quantity from linear algebra, which is called a spectral norm of the matrix A. And it is equal exactly to the maximum singular value of that matrix. We'll discuss what singular values are on the next slide. But for now, well, let's think how to make this matrix Lipschitz 1 continuous. Well, the answer is quite simple. We just divide it by this maximum singular value. Just divide each value. And then we will get 1 on the left side, and it will be it will satisfy Lipschitz continuity with L equal 1. All right? So what it takes to make the operator continuous is just the matrix continuous, is just to divide it by the maximum singular value. Now let's discuss what singular values actually are. So we can obtain all singular values via singular value decomposition. So we just decompose matrix A into matrices U, matrix U, which consists of the so-called left singular vectors, matrix sigma, which is a diagonal with singular value, squares of singular values on the diagonals, and matrix V, which consists of right singular vectors. And the important thing is that these vectors, left singular vectors, are pairwise orthogonal. So if we multiply one vector, a vector column from this matrix on another, we get 0. Well, essentially, a scalar product of them is 0. And this allows us to, instead of calculating this, because calculating singular value decomposition is actually quite hard, so it's a computationally intensive problem. And we are interested only in the maximum singular value. And this allows us to if we somehow manage to find the left and right singular vectors that correspond to that maximum singular value, we'll actually be able to get it via these two vector by matrix products. So if you want to find this maximum singular value, the problem reduces to reduces to the fact that we need to find these two vectors. And there is quite an easy way to actually find them. Let's discuss it. So it's called power iteration method. And for simplicity, instead of singular value decomposition, we'll consider eigenvalue decomposition. So we'll place some restrictions on the matrix A. It has to be square instead of rectangular, and it has to be diagonalizable. But it's just to simplify the algorithm. Then let x1 be initialized at random, but with unit norm. And then we just run the following iteration. So we multiply this vector by the matrix and renormalize the output. So its operation is just one matrix by vector multiplication and then renormalization. And in limit, if we do this iteration long enough, we'll actually converge to the eigenvector q that corresponds to the maximum eigenvalue lambda max. So for singular value decompositions, instead of one matrix by vector multiplication, we would have two. So for left singular vector u and for right singular vector v. And on practice, this actually means that we can calculate the maximum singular value or eigenvalue, as in that case, via just two matrix by vector multiplications. And I would like to point out that all the operations in this algorithm are actually differentiable with respect to A. And they're differentiable with respect to omega. So if A is actually a reshaped version of that kernel omega. So on practice, we actually don't run this iteration till convergence. We actually do one step at each gradient descent step that we do in the generator or discriminator. And we just keep the previous estimate. So we just keep the previous q or previous u and v's and use them to get a better approximation with the updated weights. So it's all good. So it seems that using this algorithm, we can actually make our neural network Lipschitz continuous, and it will work amazing, right? But it turns out that it won't. And on practice, instead of this AW, we use a different matrix. So AW has this big shape, a large shape. So it's actually a size of the output tensor times size of the input tensor. But on practice, we run this power iteration on a much smaller matrix W, which is just a reshaped version of the weights omega that I used. So it's just kernel weights that we reshape. This is kernel size, essentially. And we can prove that the resulting, if we run this power iteration for the matrix W, the resulting singular value will be a lower bound to the true singular value. And that lower bound will always be unreachable unless essentially we resolve to the linear operator. So a convolution with kernel which is equal to 1 by 1, essentially a simple linear layer. Only in that case, the singular value will be equal to the true singular value. But that seems fine, right? Because, well, this matrix is huge. We don't want to have any more computational overheads in our optimization process. Maybe this is why we use it. Well, it turns out no, because this method, this approximate spectral normalization, consistently outperforms true spectral normalization. So if you were to run this true spectral normalization method and constrain your network to be Lipschitz continuous, then well, the result would be less in terms of final quality metrics. Yes?
Yeah, maybe it's a little bit late already, but could you return one slide back?
Okay.
Yeah, here. So this algorithm with iterations, how come that it converges to the maximum eigenvector? Because just vector x can fall into zero space of matrix A, so or kernel, and then we get zero vector as a result.
Well, there are probably some constraints that I didn't mention.
Ah, okay.
But of course, well, matrix Q in that case cannot have it has to have inverse. Well, okay. So there are some constraints, but for singular value decompositions, it does not really matter. It might be a problem for that decomposition. And on practice, we usually don't consider the matrices with that values, the zero values, because we try to initialize our network to actually not have zero components, right? Well, the weights of the network. Yes. Oh, thanks for the note. So person in the first row says that probability to fall into that vector space is 0 if you take a random vector. Well, I didn't want to delve into too much details here because, well, this power iteration, it kind of falls out of the scope. So I just wanted you to know what the machinery behind it is, and truth that I don't do linear algebra, so I'm not sure, well, when it actually converges. So I'm kind of in the same terms of you right now. So yeah, another question. Can you bring the mic, please?
Thanks. So can you go back like one slide, please?
Okay.
So no, another one. The one with the maximum singular value. So here. So I think maybe, I don't know if you try it or somebody try it. Like, can you use the trace of the matrix instead of the maximum value, the maximum singular value?
Well, I didn't try that, but well, it will be also too restrictive, right? Because it.
Yes, but it will be easier to compute, I guess.
This is also easy to compute, because we do just one matrix by vector 2, actually, for the left and the right singular vector. So it's not a big overhead.
But the other one is just a product and, you know, like between two matrices. So, well, the same matrix.
Yeah, I don't have an answer because I didn't try, and I haven't heard that it actually works. So spectral normalization is actually, well, it's been around for a couple of years, and nobody tried trace. Maybe it would work. Maybe it's a good idea. So I can't tell.
Okay, thank you.
Okay, so coming back to that. So as I said before, this method of using the reshaped kernel somehow outperforms. It's not by large margin, but it actually outperforms. And the takeaway that I would like to give you that, well, it's kind of similar to batch norm, right? The original explanation of batch norm, it kind of makes sense, but its errorness, like was proven in some recent papers, so it does not actually reduce the covariate shift. And the same is like with spectral normalization. So you may consider that it actually makes your network Lipschitz continuous, but it's good to know that there is much more to that. So it's not just that, it's something more. It's maybe a good research problem if some of you are interested in that kind of stuff. Okay, so maybe if you have some questions, we can take it at that point and then get to the next topic.
Yeah, I'd like to hear a brief overview of why, how does spectral normalization works? Like, is it a special addition that we add to some loss functions? Because I don't really see why is it needed. Probably you have mentioned it and I missed also.
So how does it work? So as I said,
not exactly. Not how does it work. It is clear, but why do we need it?
So it's a form of regularization. So we try to make our operator Lipschitz continuous, and well, on practice, that makes your optimization process, this GAN game, actually more stable, and it yields better results. So the authors of that paper that I mentioned on spectral normalization, they actually applied it, and they got the boost. And since that paper, everyone was using that. So any state-of-the-art results where you have been using spectral normalization, Initially, it was suggested to be used in the discriminator, following that Wasserstein GAN logic, where we kind of constrain the discriminator. But then they also used that in generator, and it also improved the performance. It kind of does not make sense, right, from that perspective of Wasserstein GAN, but people use it, and it improves the results.
And without it, we can probably we can still get the result, but it will be noisy and the optimization will be unstable.
No, well, people lived somehow before that paper, so there are some results. There was, for example, DC GAN, it kind of works, but it just makes it better. So if you just put spectral norm in DC GAN, for example, the convolutional GAN, it will make it better.
Thanks.
And the important thing is that it's a rather simple addition. It does not introduce a lot of computational overhead. So now we discussed before that it kind of does not make sense to treat that optimization problem that we do in GANs as minimization of the divergence by the discriminator or by the generator. Just because it's not feasible to actually converge with respect, well, let's take the objective. Let's take a look at the objective. It's not feasible to actually solve this internal minimization problem and to converge with respect to discriminator. It's actually, well, computationally intensive, but even worse, it works worse than if you actually do it like they do in practice. So let's take a look one more time. In theory, it is suggested that we first solve the optimization, the inner optimization problem till convergence. We get the optimal discriminator. Then we take a single step down the gradient with respect to the generator, and then we do repeat the steps all over again. And this with optimal discriminator can be considered as a divergence between the two distributions. So generator minimizes that. But we have seen this slide before that actually for most of the divergences, if we find actually the optimal value, it will actually be constant and the gradient will be 0. So we won't be able to actually run this optimization algorithm if everything worked like it is in theory. But on practice, of course, we have a finite capacity discriminator that is not able to fit the divergence correctly. We get some estimate of that divergence with non-zero gradients. But in practice, actually, we do something completely different, right? Because on practice, we actually do a single step of the optimization of the gradient ascent in the inner optimization problem, interchanged with a single step of gradient descent with the outer optimization problem. So in a sense, this L that we use to optimize the generator, it's not divergence, it's lower bound on divergence. And we minimize lower bound on divergence. Well, I'll let it just sink in a little bit because it's kind of doesn't make sense, minimizing a lower bound on the function. But moreover, this approach in practice, it actually works much better than the approach suggested in theory. And I didn't manage to embed these videos into my presentation, so we'll just look at them like that. So here we have a simple problem, right? We're trying, this is the distribution of our generator. So it's just I kernel smoothed the outputs of the generator. And this is the target distribution that is trying to match. And well, generator and discriminator are both some multi-layer perceptrons, essentially multi-layer linear networks. And also I evaluate the classifier output, so discriminator output at each point in order to visualize how it actually changes. And let's take a look with the divergence. So well, first of all, in the first step, we get some already trained classifier because we perform this training at each step. But we can see that the convergence process it kind of does not work. It even doesn't match the distribution shape. You have seen the same example before when I showed you the convergence of the, essentially the same example, but the previous one in the previous part of the lectures. And let's, take a look at it one more time, probably. So just to remember, of course, there will be this where the discriminator kernel does not train, but in the end, well, it trains everywhere. Because, well, it's also a network that we have that has to converge. But let's consider the second way. Sorry, spoiler alert. let's consider the second way. Well, a spoiler alert, it actually works. Let's consider the second way of optimization. So as we can see, the discriminator is actually not sure almost everywhere about its prediction. But actually, this scheme does make the generator to converge and to actually match the distribution. And it kind of makes sense, right? Because in the first part, so each sample of the generator, only a handful of samples would actually get some gradient. Because for most of the samples, the discriminator will be just overconfident. It just say that, well, it's a bad sample, 0 gradient. I'm quite sure that it's sample from the generator. And you're not training, right? In order to training, the discriminator has to tell, well, you have this sample is kind of more fake, and this sample is kind of more realistic. And this allows the discriminator, the generator, to train more smoothly. But this completely throws away that logic of optimization of the divergence. Because, well, we're doing something different. OK, back to the slides. And if we view that, so actually what we're doing here, we can consider that as a game, as a two-player game. There is the generator and the discriminator. They have some min-max problem. They have some differentiable objective that we're trying to solve with the method that was used in game theory to solving exactly these differentiable problems. So this method is called alternating gradient descent. We do an optimization step over psi, and then we do optimization step over theta. And well, if we consider some theory, well, game theory, what it tells us about that optimization method, it will tell you that it will not always converge to the saddle point. It will not always converge to the values theta and psi that are optimal. So remember that picture when the distributions are matched, the discriminator doesn't know where is a fake sample, where is a real sample. So this ideal picture, it may not happen. So this is like a saddle point, but theory tells us that this algorithm does not always converge. And there are some recent papers that explored that topic. And for that, we need to simplify our objective a little bit because, well, it's quite hard to consider the dynamics of that game for this multidimensional problem. So first of all, we're going to reduce the first expectation, first distribution to the delta function at 0, and the second expectation delta function at theta. So it's a similar example that we had in the last part, on the last slide in the previous part of the lecture. So and also, so the generator is actually a single parameter. It's a single parameter theta that is trying to tune. And the discriminator also has a single parameter. It's a single parameter psi that it's trying to tune also to classify for some function f. Well, of course, since this x is always 0, this quantity, this expectation will be just f of 0. This expectation will be f of psi theta. And since we're solving the optimization problem with respect to these quantities, we can just consider this one. OK? So for this simple problem, would the optimization strategies that we use, the alternating gradient descent, make for example, for different functions f, do we achieve the convergence? Do we arrive at saddle point? And well, there is a paper that have run the experiments, and these are experiments for the non-saturating GAN. Essentially, well, the GAN proposed in the original paper, it's a slight modification over that Jensen-Shannon divergence. Well, a slight twist. We'll consider that on the seminar. You will have to implement that. So you can see that on x-axis we have thetas, on y-axis we have psis, and you see that it kind of goes around the orbit around the point. And it actually takes a lot of time to converge, and in reality it does not even converge to that point. So it ends up at some orbit around this saddle point. And for Wasserstein GAN, it's even worse. So if we apply Wasserstein GAN with gradient penalty with the problem that I've discussed before, it will actually not converge at all. It will just go in orbit, around and around, like in infinity. So it will just repeat itself. And well, this dynamic is what people who apply GANs on practice have noticed a while ago. So in practice, how that happens is that if you evaluate some quality metrics on your, for example, model, the quality metrics do not improve, but the samples kind of differ from one iteration to another. Weights differ from one iteration to another, but the quality does not improve. So in practice, we have had the situations, well, we realized that these situations exist before this paper appeared. And what can you actually do? It seems that if you can you reduce your orbit somehow and get yourself closer to the saddle point, well, it will kind of make the predictions better for free. And there have been developed, well, some engineering methods and some more theoretically grounded methods in order to address that problem. So the first method is exponential moving average. So let's consider a saddle point. The coordinate axes are the same like in the previous example. So you imagine that on the x we have thetas, on the y's we have psi's. And so we run our optimization method, and we arrive at some trajectory that ends up being an orbit. So it's end up cycling in itself. So just to remind ourselves that these weights are actually, well, vectors. And what we could do in test time, so this happens in train time. We don't well, interact with it in any way. But in test time, instead of taking, well, the final value that we arrive in, well, theta final, right? We could take the moving average of the thetas that we got in train time. So this is theta e plus 1. So we take new theta e from that orbit with some weight alpha, and we accumulate the previous, well, no, it's essentially exponential moving average of the weights of the network. And how does this look? So instead of theta e, we actually take, well, this is like initial vector, right? Well, initial value for that theta hat. We take it with some value 1 minus alpha, and then the next value we take, the next weights we take multiplied by alpha. And you can already see though from this toy example that we kind of arrive closer to the saddle point that we were before. So we're kind of reducing the radius of that orbit. We can do that iteration one more time. So take this theta 2 multiplied by 1 minus alpha, take the new theta multiplied by alpha, and arrive even closer. So you see that the radius at which this point sits is actually smaller than the radius that we had before. So of course, this is all toy examples. On practice, this is slightly more complicated, but just to give you the idea of what happens. And on practice, we'll just spiral onto some lower orbit. So an orbit with lower radius, which will still go around the saddle point, but it will be closer, and hopefully we'll get better quality from that. So this method just reduces the radius of the orbit. And a good thing is, because it was like, it's kind of engineering feature, it works out of the box. So you can just run it. Well, you can just start training your network, and you start accumulating these moving averages. And after you stop training your network, instead of taking the weights, you take the moving averages and evaluate them. So there are no parameters to tune. Momentum is usually set to the momentum, well, similar to the momentum in Adam optimizers that you usually use. So this is like a practical approach that has been, well, all the state-of-the-art results from what I know in GAN synthesis, they utilize this trick. So like spectral normal, it is used by everyone. Another trick that is more theoretically grounded but addresses the same problem is weight averaging that was developed by the colleagues, jointly by colleagues from, well, they developed it jointly with someone else, but the colleagues from the Bayesian lab actually worked on this. So consider, again, the orbit around the saddle point, and consider that every weight inside the orbit has, well, essentially assume that we have accumulated all the weights inside this orbit. Well, is there a way for us to actually arrive not at the smaller orbit around the saddle point, but exactly at the saddle point? Well, the answer is quite simple, right? We could just average all these weights and arrive exactly at the point. So if we take exactly average, we, in theory, get even a better boost to performance than we had before with the exponential moving averaging. But of course, the problem is that when to start averaging. So you have to first detect that you arrived at the orbit, and then you have to detect that you're actually cycling. And you will not get into the exact values. You can't detect the cycle. So it's kind of tricky how you do it. So on practice, the authors suggested to just stop the iteration at some epoch, and then just for some epochs, you just accumulate weights and then take the average. So this approach is a little bit trickier than the previous one, but in theory, it gives you much more benefits if you apply it. All right. Any questions regarding this part? Yes? Wait for the mic, please.
Just to confirm, so these methods are used during test time and not during training time?
You have to accumulate averages during train time.
Yeah, of course, but okay.
You do not differentiate for that.
Okay. Okay, thanks.
Okay. So that's it with the helpful tricks. Of course, if you want your GAN model to work out of the box, the best thing you can do, just git clone the state-of-the-art model and just use all the tricks that they used. But the two tricks that I mentioned, the two problems, they, I think, give you the most benefit out of all the tricks that you could use. So, yeah.
Yeah, actually, there's still a question that I have about the power iteration approach to spectral normalization. Because what you want is a Lipschitz one continuous function, right? You want to upper bound the Lipschitz constant, but the power iteration gives you a lower bound to the spectral norm. So,
yes.
How do you check or enforce that the function is actually Lipschitz one continuous? If you only have a lower bound.
Yeah, that's
and not
a
an upper
good
bound.
question. So the question is, why, if we apply this power, well, it's not about this weight averaging, it's about spectral norm. Again, what happens? Well, we apply the power iteration only once. And essentially, we also get this lower bound estimate on that singular value. So essentially, we assume the neural network to converge and to wait to stop changing by a large margin. And since you keep the estimate of the singular vectors from the previous iteration and your weights don't change much, essentially you run this power iteration multiple times on the similar weights vector. So the matrix A, assume that that does not change, but the vectors U and V, you keep them and you update them constantly. So at the end of the training, you kind of get the Lipschitz one function.
Okay, but I mean, still it converges from below. So you only have a lower bound, so you're not actually guaranteed Lipschitz one continuity?
It's not guaranteed. As I said before, it's not even guaranteed because sigma tilde that we use, the approximate one, is just a lower bound for the true sigma. So it's just an intuition, essentially. When people write papers about spectral norm, they provide you this good theoretical explanation. So I just wanted you to realize that it's not guaranteed. Yeah. So the point that you mentioned is, well, it's not as bad as the point that we are not using this A omega matrix, the full matrix, but the reshaped matrix, because we kind of converge, so we kind of run this power iteration in the end multiple times, and in the end we get something close to Lipschitz one, but, well, this is also like a caveat, but it's a more like engineering one, so all the good methods, they usually have some engineering that is not explained.
Okay, but then in the end, you're not solving the true dual.
Yes, of course not. It's just a way to regularize.
Okay.
There is no theoretical reason why we would want Lipschitz one function. It just works. It's just a good regularization.
Okay, thanks.
So our saddle points resides in a space with a different metric than the Euclidean one. So the saddle point will be in the space of the loss function, right? So my question is, does this averaging in the Euclidean space of the parameters actually finds the saddle point on a manifold that might have a different metric?
Well, that's a good question. Of course, it's even hard to find the orbit. So on practice, you will never get the saddle point because it's hard to detect that you are in the orbit.
And it is the same for the other technique as well.
Well, the other is kind of more theoretically grounded, but you get less benefits by doing so. You just reduce the radius of the orbit. You are guaranteed to arrive closer to the saddle point, but it's not guaranteed that, well, you will actually arrive at the saddle point.
Well, yeah. Thank you.
Okay, so next questions we'll probably take at the end of the lecture and during the break. So there are two topics that I wanted to discuss, the quality measurements, and so it's about essentially telling, how can you tell if your GAN is good?
Sorry, I have a question.
Can you ask it after, because we have only 15 minutes left. Thank you. So all automated metrics, so essentially metrics that you can quantitatively evaluate, they kind of suffer from being bad. So in the sense that when you do classification, you have accuracy. So accuracy is like your best goal that you want to maximize. If you are not satisfied with accuracy, you could consider F-score, tune it a little bit to satisfy your practical applications. And we would really love our classifiers to actually maximize accuracy, right? So this does not happen with GANs. In GANs, we don't have that good metric that we really would like to maximize, because all metrics suffer from like trade-offs, essentially, enforced by the metrics themselves. And we'll discuss a little bit about it. And if you actually want to apply your GAN to your practical problem, let's say, the best bet that you could get away is just to design your custom metrics that suits your problem. For example, if we try to synthesize realistic images that would be likable by humans, the best metric that we can get is just asking humans, are the images good or not? So not evaluating the metrics that I will describe in the next slides, just asking users. So we trying to evaluate our end goal. And this is like the problem with the, that kind of restricts the comparisons in the field, because when we publish papers, we kind of run all these user studies all over again, and there is like no metric that we could easily evaluate and compare to each other. But for images, since I work mostly with images, I can discuss some of the metrics that are actually used. So the first one is called inception score, and it evaluates the objectiveness of your outputs of your network. So let's assume that each output of your network has a single object in it, and the overall distribution of these objects is uniform across all your data set. So you kind of force your network to predict the images like that on the left, where you have a single object on a uniform background, and prohibit it from synthesizing multiple objects with occluded backgrounds, well, something complicated. And this is kind of tied up to ImageNet and ImageNet classes, because we usually use pre-trained networks pre-trained on ImageNet in order to evaluate these losses. So more formally, what we want to do, we want so first of all, in order to evaluate inception score, you take some pre-trained network on the ImageNet, you generate some samples, and you run this network on the samples to obtain the probabilities of each class from the ImageNet. But this does not have to be ImageNet. So you have your network in your field that has pre-trained to classify some samples from your field, for example, biomedical images, etc. You can use that network. So there is no restriction on that. So for each single image, we want the prediction of this network to have low entropy, to be spiky. Essentially, this network has to be sure that there is one particular object, and the rest is like low probability. But for the collection of the images, we want the marginal distribution of Y to actually have high entropy. So the whole collection of the samples has to be uniform. So our network does not have to fit only one mode. It has to fit all the modes, so all the variety of images in a data set. And so logarithm of inception score is actually this. It's expectation over X of KL divergence between this conditional distribution and marginal distribution. So let's see how actually this enforced into this. So first of all, the definition of the expectation is the sum over X of P of X by the quality inside. And the definition of KL is following. So it's sum because we have the discrete distribution. Then logarithm can be separated into, logarithm of the fraction can be separated into two terms. The first term, we just take logarithm of P of Y outside, alongside with sum over Y, and this we bring inside. And you can look it up. So here we actually have a joint distribution on P of X and Y, right? Because conditional is just joint divided by X, P of X. So this cancel out. We got P of Y, logarithm P of Y, and this is entropy. So entropy goes with plus because we want high entropy. And the second term, we take this logarithm of the denominator, we bring P of x inside, and, well, you can also look it up on the Wikipedia. That's the definition of the conditional entropy. So we just have to rearrange that into like P of x and y divided by P of x. And this is like exactly the definition. So we want to minimize low entropy. So we put high entropy with plus, and this with minus. So it's kind of straightforward, this metric. But this metric is restrictive because it does not account for the data set. So there is no data set that you trained on. You just only evaluate the samples and compare them to some ideal distribution of these class labels. And this was addressed in another metric, which is called Frechet inception distance, which measures the overall quality, about how your images match to the images in the data set that you trained on. And long story short, we just compare the activations of a pre-trained deep neural net between real and fake data sets. And we only compare means and correlations. So it looks like this. So we take the mean of the feature maps over real images, substitute mean over generated, square it, so we penalize the difference, and then we penalize the difference between the correlation matrices, calculated over real and the fake data. So it's also kind of straightforward, and it also enforces the bias in terms of the data set that the network that you use was trained on. So if you train on ImageNet, you use the network, if you use the network pre-trained on ImageNet to evaluate biomedical data, then it probably is not a good metric to use. So you have to use features of the network that was pre-trained for your specific task. Well, if we are talking about photorealistic images, for example, faces, it may make sense to use FID still, because, well, there are some faces in the ImageNet, and the overall image is kind of consistent with what images are in ImageNet. So now I'm just going to go to the conclusion, so you can ask the questions about this previous part after the lecture. Question is, so you may think that GANs actually bring a lot of drawbacks into, compared to VAEs, for example. In VAEs, we have access to everything. We have access to all the density functions that we are interested in. We can evaluate them. GANs don't have any of that. They just essentially provide you samples. But I would like to point out that these samples are actually very good. So this is a fun picture that Goodfellow posted on his Twitter. It's just progress over the years in terms of image generation quality. So we started like 5 years ago with this, and now we have this 2K resolution samples by style GAN model, the so-called. And what unites all these models is the size of the latent space. So the latent space is actually like 512 digits. And 5 years ago, we were able to encode only that blurry image into these digits. Now, we are able to encode the full image with a lot of details, a lot of personality that is represented in the same size of the latent space vector. And the progress in quality of the outputs, and from what I know, VAEs are still behind in terms of quality, the quality of the produced samples. Even the newer models, they still, do not compare or surpass the state-of-the-art GAN models. And this quality actually translates into the quality of the output, actually translates to the quality of the inputs, to the quality of your latent space. For example, if you take the model that was on the right that produced these highly realistic images, fix it, and just train an encoder into that latent space using the same data set, essentially. Reverse that network after it was trained. You can, achieve something like that. So it's a reconstruction of the Mona Lisa painting via that GAN network. And moreover, you not only have access to a good latent space that has a representation for most of the images, even the images that were not in the data set. You can actually perform some meaningful manipulations with that latent space. For example, you can rotate that image. You can, for example, make the Mona Lisa more manlier or make your smile. So you can just perform some basic arithmetic in that vector space. I'm not going to delve into details about how it is done. I just wanted to point out that the progress in terms of outputs of GANs do not only result in fancy pictures, it results in the progress of how we actually learn that latent space. And in a sense, GANs can also compete with VAEs in that sense, in that regard. So VAEs also learn the latent space, and well, the latent space learned by GANs is actually also improving by quite a large margin with each new result which appears. And another thing is that, I'm sorry. Okay, I took this video from Twitter and, well, okay, let's take a look one more time without sound. So this is an example of the newest NVIDIA model. Essentially, it's a drawing tool for you. And what it does, what this model does in a nutshell, it takes a segmentation map, or in that sense, in that case, a doodle that you draw. But in training, it takes segmentation map, and it just translates it into an RGB image. So there is no generation part, there is no sampling part. It's just a regression problem. You want to take this image and translate it into that image. But it turns out that, well, you have the ground truth essentially, well, for most of the applications like that. But, well, you can just introduce your GAN objective, objective inspired by GANs, this adversarial objective. You can still introduce a discriminator that will try to discriminate the synthesized image from the stack of the real images, and you will get better results, even for that simple regression problem, where you think you have ground truth, you have a simple problem, map this input to the ground truth. But it turns out that introduction of adversarial term actually helps you to get better images in the result. And so the applications of GANs, they range, now I think most of the applications, they're not about sampling, they're not about generating, they're about essentially the trainable objective that you can use to regularize the training in your supervised problem. And this is where like the most amazing results nowadays come from, well, especially this one. And so the takeaway is that, as I said before, GANs are these powerful models that achieve state-of-the-art quality of the output images. And this, this quality of the outputs actually translates to the quality of the inputs. So you can train GAN, and then you can do whatever you want with the latent space that you have trained. So the latent space that actually encodes a lot of details, for example, for the face images, these 512 digits have compactified representation of the image in terms of information. But still, this is a very active research area, so it's by no means like depleted. So there are multiple open problems. Like anywhere in deep learning, we don't know why everything works. So an attempt of explanation of that is actually required, and we need more theory backing these amazing practical results. And if you're keen on applications, you can essentially try applying these generative adversarial networks, this framework, not as without generative part, just adversarial training to any of your supervised problems, and actually you may get better results and benefit from that. So that's it. Thanks for listening, and I hope that was useful for you.